Vector algebra.
All right, class. So, under this is a whole new chapter altogether, and I want you to understand also with. So today we'll be looking at vector algebra. Today we'll be looking at vector algebra. Vector algebra. All right. So now, in terms of quantities, we have two of them. Anytime you see quantity, you have two. You either can see a scalar quantity, or you can have what? A vector quantity. Now, what happens is that the difference between the two of them is that scalar quantities, they have only magnitudes. Scalar quantities, they have only magnitude, but vector quantities have both magnitude. Vector quantities have both magnitude, and they also have what we call direction. Vector quantities, they have both magnitude and they have what? Direction. All right. So now what happens here is that when you have a vector, vectors are also always represented by what? Arrows. So now what happens is that the length of the line is considered as what? The magnitude of the vector, and the arrow here represents the direction of the vector. The arrow there represents the direction of the vector. So anytime you have a vector like this is how it represents the vector diagrammatically. This is how it represents the vector diagrammatically. All right. So now, if I have a point A over here, and the point moves from A, and the direction moves from A to B, this is a vector, but this vector can be described as what? AB with an arrow on top that is facing what? B. But what happens here is that if I have a vector of this nature, V, as my vector, and I change the direction of the vector, that is, I change the direction of the arrow, the change of the direction of the vector will negate the vector, and it will only affect the vector in respect to its direction, but will never affect the magnitude. Now, when you change the direction of the vector, what happens is that magnitude is always the same. So it's something you should also get in your head, or it's something you should understand. Anytime you change the direction of the vector, magnitude is not affected. The magnitude is what? Always the same. All right, so now, if I have vector this way, mathematically, I can present it as what? Vector AB to this direction. Again, to take note, if I have one vector, if I have a point vector, let me just say it that way. A point vector is always from an origin. So now when I draw my Cartesian plane, this is an origin 0. So if I draw a vector from this particular origin to, let's say, a point P in the direction towards P, a point that vector is always from what? An origin. So I'll get what? OP direction to that. So that vector will be described as OP direction to that. And that is a point vector. But anytime the vector is also from another variable, you have to put the variable over there. Now, a zero vector is the only vector with no specific direction. Anytime there is a zero vector, you have to put in your head. You'll notice somewhere. Zero vector has no specific direction. Has no specific direction. Has no specific direction. Now, there's one thing you should also understand. There is something we call the Euclidean space. The Euclidean space. Now, the Euclidean space actually describes to us the dimensions that we can have in terms of vector per our standard. So now we can have the coordinate system that give us maybe the two coordinate system in a Euclidean space, or we can have the three coordinate system in a Euclidean space. So now the Euclidean space is more or less like a dimensional space. So now we can have the 2D existing in the dimensional space. We can have the 3D and the 4D that is above our natural way of seeing. So we understand that the 4D is above. But per mathematical principles, in vector space or vector Euclidean space, you should be looking at the 2-coordinate system and the 3-coordinate system. So as we further on, you realize that sometimes I write V2. So when I write V2, you should understand that I'm talking about the 2-coordinate system, a vector in a 2-coordinate system, that's in the 2 Euclidean space, or sometimes I write V3, which will describe a 3-coordinate system. Now let's look at combining vectors. All right, let's look at combining vectors. Combining vectors. Okay, so now I want to make it very simple for you to really understand it, the combining vectors. After that, we look at the vector addition. So I want to make it very simple for you to understand. Now, what happens here is that with combining vectors, but before that, you should know that a vector can be what? Horizontal. A vector can be what? Horizontal. We can have a vector which is what? Vertical. You can have a vector which is vertical. You can also have a vector which is what? Inclined. Now, anytime you have an inclined vector, there are ways you can go about it. One, you have to resolve the vector so that you get, after the resolving, you get the horizontal component and you get what? Vertical component. Before you can do what? Your vector addition. Before you can do what? Your vector addition. Alright. So now with that said, I want to do this over here. If I have this diagram over here, alright. Now if I have this diagram over here and I say this is I describe this point as A, I describe this point as B, and I describe this point as C. Now, I want to move from A to C. I want to move from A to C. So I can move from A to B, and I can move from what? B to C. Okay, so you got how I place my arrows. Please don't go and put the arrows anyhow. If you put the arrow this way, you are wrong. Because the inclined one is moving on to C, so all of them should point to the C direction. So now, what happens here is that this is the resultant vector. AC is the resultant vector. So now, anytime I want to combine two vectors to get my resultant vector, I can move from one vector A to B plus B to C, and I'll get to my resultant vector AC. Please, what I've done, this should be the simplest concept you should have in the beginning here. If you understand this very concept, everything that we'll be doing again will be what? A bonus to you. So now, the vector addition over here, A to C is equal to A to B plus what? B to C. Please, you should get it. So now, as I said, take anytime you are given a vector A, B, and let's say, okay, let me just use other variables. You are given X, Y, and Z. And they say XZ is the resultant vector. XZ is the resultant vector. So generate the combining vectors. Generate the combining vectors. You should simply understand that if they are combined, then XZ is therefore equal to X, which is starting XY. XZ must go to Y first, plus Y going to what? To Z. I get it. So you should get the trick in doing that one, and that is our combining what? Vectors. Now let's look at vector addition. Now with vector addition, we have the triangular law of adding vectors. We have the parallelogram law of adding vectors. I'd just like you to go and look at that. There's the triangular law of adding vectors, and there's the parallelogram law of adding vectors. Now, if you have two vectors, if u and v, if you have two vectors which are u and v, and these vectors are positioned so that the initial point of and if these vectors are positioned so that the initial point of v, the initial point of v is the terminal point of u. So now I have these vectors. And this vectors is what? U and v. So now these vectors that is positioned over here, the vectors are actually positioned in the sense that the initial point of the v that starts from this point, let's say this point is A. So let's say A, B, C. And you have vector U and you have vector V. And we say that the initial point of this particular vector, the initial point of this particular vector here is of the particular vector V is the terminal point of U. So now what happens is that when you start from here, you end at B. But the B point here, it is the initial point of what? V. V will also start at B and end at C. So now if you want to add these two vectors, it is very simple. The resultant vector is what? U plus what? Plus B. So now if your U here was a vector of A mapping to B, and your V here was a vector of B mapping to C, then your U plus V, which is a resultant vector, and your U plus V should be the resultant vector, which is what? AC. Then your AC vector is equal to what? Your U plus V, which is also equal to what? Your AB, vector AB, and vector what? BC. Alright, so this is the first instance. Now there's also another instance where the vectors will be inclined, but they will not position this way. The two vectors will now move from a particular point. They will all move from an initial point. Let's say this initial point is A, where vector U and vector V will all move from this initial point. So now if vector V, U, and V are all moving from a specific or a particular initial point, what happens is that you have to complete the shape in terms of a parallelogram. You have to complete the shape in terms of a parallelogram. And now when you complete the shapes in terms of a parallelogram, you can draw a diagonal line to meet two ends of the parallelogram from their starting point. And now that diagonal line will be your resultant vector, which is your U plus V. That diagonal line will be your resultant vector, which is your U plus V. So in terms of the parallelogram law of vectors, you consider the angle that will be created here. But first of all, you know the angle that will be created here. If you take that angle from 180, you know the angle that will be created here. So now if I say here is alpha and here is beta, beta will always be equal to 180 minus what? The alpha in the parallelogram law. So if you take that angle out, then you know what will be created over here. So now to find your resultant vector addition, the U plus V, it is always equal to what? Your vector U squared plus your vector V squared minus 2 times vector U times vector V cos of the angle beta. And this is known as what? Your cosine rule. This is known as what? Your cosine rule. Okay. Now the third thing we want to look at is scalar multiplication in vector algebra. The scalar multiplication in vector algebra. Scalar multiplication. So now, with scalar multiplication in vector algebra, we want to consider the fact that if you have two parallel vectors, A and B, if you have two parallel vectors, A and B, then there must be a number C so that A can be equal to the number C times B. Then there must be a number C so that A can be equal to what? A number C times B. Now we should note that two vectors are said to be parallel if one is a scalar multiple of the other. So now, if you have A and B as two parallel vectors, that is to say, A and B are all parallel, all vertical vectors, but they are parallel to each other. Then we can say they are parallel to each other when one is a scalar multiple of the other. And here, the C here is referred to as what? The scalar, because that is representing the scalar multiplication of the particular vector. So now what happens is that anytime you have these vectors, you can say U minus V So anytime you have a vector negating itself, you can say u minus v is the same as u plus the negative of what? Of the vector v. So now, if you have one vector going this way and the other vector going this way, v, and you have this vector as u and this vector as negative v, and you want to add them, then it's simply what? U plus what? The negation of the vector v, and that is the same as what? U minus v. U minus v. Now, the last thing we want to look at is the components of a vector. The components of a vector. Okay, so the last thing we want to look at is the components of the vectors. The components of the vectors. All right. Now, we can have vectors in a coordinate system. We can have vectors in a coordinate system. And before that, I said that before you can know the vectors in the coordinate system, you should actually have an understanding of the Euclidean space. And in the Euclidean space, you can have a 2-coordinate system. And in the same Euclidean space, you can also have a 3-coordinate system. So now, the vectors in the coordinate system, we can have the 2-coordinate system and 2. We can have the 3-coordinate system. So now, if you have the vector as a 2-coordinate system, then example is what? A, B. So this is a particular vector in a 2-coordinate system. And in the same way, you can have a vector in a 3-coordinate system as A, B, and C. This is a vector also what? In a 3-coordinate system. This is a vector in a 3-coordinate system. Now, let's consider a position vector. Let's consider a position vector OP. In a 3-coordinate system, let's say A1, A2, A3. So this is a position vector OP in a 3-coordinate system. And let's consider another vector AB over here. AB over here, which has its initial point starting at vector A. It has its initial starting at vector A and the terminal ending at vector B in this direction. So the vector A here will have also coordinates x1, y1, z1, and the vector B here, which is the terminal vector, will also have coordinates x2, y2, and z2 over here. So let's consider this position vector and this vector over here. Now what happens is that when you have something like this, then we must have, or we can say that x1 plus a1 should be equal to our terminal vector here, x1 plus a1. So we consider this same point as what? Our position vector P. So you can say x1 plus a1 should be equal to what? Our terminal vector here, x2. Alright? And you can also say that our y1 plus our a2 should be equal to our terminal vector y2. And you can also say our z1 plus a3 should be equal to our terminal vector z2. Now when you have this, we can then say that our a1 is equal to x2 minus x1. You can say our a2 is equal to what? y2 minus y1. And you can say our a3 is equal to our z2. Our a3 is equal to what? Our z2 minus what? z1. So since you are having this, then if you want to find the resultant A, that is our a1, a2, a3, if you want to find our resultant A, then our resultant A is very simple over here. We can say a1 here, which is x2 minus x1, a2, which is y2 minus y1, and a3, which is what? z2 minus what? z1. This will give us our resultant A. This will give us our resultant A. Alright. Now this is something you should put in your head in solving a lot of questions. I want us to look at one question. Alright, so this is the question I want us to look at. Okay, so it says that we should find the vector represented by the directed line segment with initial point A and with what? A terminal point what? B. We should find the vector represented by the directed line segment with initial point A and a terminal point what? A. Terminal point B with these what? Vectors. And this is a particular vector that is having what? A 3-coordinate system. It's a vector that is having what? A 3-coordinate system. A vector that is having a 3-coordinate system. So what do we do here? It is very simple. If you want to find the vector represented A to B, if you want to find the vector that is represented here A to B, it is very simple that it is always the B minus what? Over the A. So now you take the minus 2, which is x2 minus x1. x2 minus x1. Alright, so that's the equation. Minus 2 minus what? 2 over here. We come to the second one, we have 1 minus what? Minus 3, which is 1 plus 3. And the last one, 1 minus 4. 1 minus 4. So your final vector will be represented as what? AB, which is what? Negative 4, which is 4, and what? Negative what? 3. And this will be your vector represented by the directed line segment. Now, the length of a 2-dimensional vector. If you want to find the length of 2-dimensional vector, if you want to find the length of a 2-dimensional vector, that is to say, you have a vector A that has points A1, A2, and you want to find the length of this 2-dimensional vector, it is simply equal to what? The square root of what? A1 squared plus what? A2 squared. It's simply equal to what? The square root of what? The A1 squared and A2 squared. In the same way, for 3-dimensional vector, A having A1, A2, and A3. For 3-dimensional vector, the length of the vector is equal to what? The square root of what? A1 squared plus A2 squared plus what? A3 squared. And this will give us the length of the 3-dimensional vector. Try and get a lot of examples and rehearse your hands on it. Thank you very much for vector algebra.